Okay, so in this lecture, we are going to introduce the idea of clustering. I've already hinted at this idea in previous lectures, especially when I was talking about the k-nearest neighbors algorithm and recommender systems. But those were cases where we knew the labels to the data that we had. So the feature vectors that we were looking at, the labels were like the movie names, right? But there are often times where you have feature vectors measuring some quantities that you don't know the labels ahead of time. And you wish to put the vectors into groups if you can find the groups at all. So one example would be, suppose you have, let's see, last fall, I was a part of a double-blind study for COVID. I was injected with either a placebo or with COVID antibodies. And every visit I went in, which was every other week for about 6 months or something, they would measure a lot of stuff about me. They would take my blood, they would take my weight, they would ask me several questions, they'd take my temperature, and all of that information that they were gathering about me could be put into a vector, right? Now, I wasn't the only one in this study. There was hundreds and hundreds of people that were also in this study. And they had the exact same information being taken from them and then stored in, you can say, a vector, right? So after doing that, it might be beneficial to know if there were any adverse effects of this, either whatever they gave me, whatever they shot in my stomach, for a particular group of individuals, but they don't know how to group the individuals into super affected by it wasn't a vaccine, it was something, but they didn't know ahead of time if they needed to group the individuals. So this would be a clustering problem where you want to look to see if there's clusters that exist and why these clusters are different, okay, amongst these people. And I'm pretty sure this type of problem happens a lot in medical scenarios. So it is very applicable. So for simplicity, let's suppose that our feature vectors that we're measuring for our patients, and we're doing a study now. Let's suppose that we're doing a study. Suppose that we have feature vectors with 2 entries. Okay, just two-dimensional vectors, right? So then we have a measurement for like temperature or something, and then we have a measurement for like, I don't know, white blood cell count or something, right? And when we plot these vectors, these points in space, we see something like this, like okay. And we see that there might be some type of partitioning happening here, where these might belong to a group, these might belong to a group, but we're not sure if there's maybe 3 groups hidden in there. There could be 3 groups hidden in there. Maybe there's more than 2 groups. Maybe it's just 1 group. But one way to cluster these vectors together, or to test out clusters, like, is to do something called k-means clustering. Yeah. Okay. And we don't know the labels. Like I said, we don't know if these patients are grouped into high risk, low risk. We don't know what they are, right? We just know that we've measured some temperature and white blood cell count, and we have this collection. And now we're going to try to put these patients into groups for maybe like a sub-study or something. So what do we need? So as input to our procedure, our algorithm, we have a collection of vectors. Okay. We have this collection of vectors. And we also have and a choice of k. And this is just some natural number. Okay. And how does the algorithm work to cluster these things? Well, we're going to introduce the notion of a center. So, so this is not as input, this is what we're going to make. Choose maybe C1, CK as a collection of initial centers, center vectors. So each of these is an in vector. So if the vectors we're looking at are in vectors, these are in vectors as our features, then our centers will also be in vectors. Okay. All right, so I'll use maybe red is my centers. So the choice of this is actually non-trivial to initialize your centers, but I'm just going to put them like maybe like here, here, and here. So initially those will be our centers. So I chose K to be 3 in this case. Okay. Okay, so next, we're going to assign each vector in our data to the center that is closest using the 2 norm that we learned about in a previous lecture. So next, I should be labeling these. 1, 2. So next, we're going to assign each vector in our data set to the closest center.
Just to be clear, the centers don't have to be vectors in our data set. They can just be vectors that we choose.
Yeah. So for example, like these were just like random vectors I chose. Our data set's in white, and then I just made those outside of it. You can choose the centers to initially be vectors in the data set, or you can choose them to be rounded. And again, that's something that you would cover in a machine learning course. That choice is actually not so simple of how you choose the very first centers. But without going into those details, we can still, with our knowledge that we've learned so far in the semester, we can still program this algorithm, this clustering algorithm. It's very simple. It's just based off of distance between vectors. Please, by all means, speak up at any point you have questions about this. So assign each vector in our data set to the closest center. Yeah, so that's just the next step. And again, remember that vector distance is the 2 norm between the vectors. So that's how we're going to measure distance. Okay. Now, all right, 3. We're going to now, so actually we should probably assign here. So like, it looks like this one is close to that one. So I'm going to draw a line to illustrate that they've been assigned to the corresponding center. The line is not a vector or anything like that. It just means that like that one's close to that one, closest to that one, close to that one. These all look like they're going to be close to that one. Yeah, these are all assigned there. That one, however, looks closer to that one. Oh, that one's maybe there. And these look like they've all been assigned that way. So that's like part 2 of the algorithm. So these have been assigned this, these have been assigned that, that's been assigned that. So I'll call this like center 1, center 2, center 3. Okay. So you should probably be thinking to yourself how you would do this assignment. Well, you would just like for this vector here, that data entry, you would calculate the distance to that, and that, and you'd see, oh, it's the shortest to there, so then you would assign it that. And then the same thing would happen there, so forth and so on. Okay, so next, we're going to update our centers. We're going to make new centers. And how do we do that? Well, actually, I'm going to introduce some notation. Maybe I'll even use the notation that your textbook uses. What do they use? I'll say let J I sub I denote all vectors assigned to center I. Okay, so that's the notation we'll use. So all of these are in J1, all of these are in J2, and all of those are in J3. Okay, so far so good? Any questions? All right. So now we're going to update our centers. Okay, and the way that we're going to do that is we're going to take the average vector for cluster 1, cluster 2, and cluster 3. Those will be the new centers. So what is the notation that your book uses for average? I think no, they just use the average of a single vector. Basically, you want to say center 1 is going to be updated to the sum of all vectors x, and so that x is in J1. Oh, and then divided by the number of things in there. So this is just the number of vectors in J1. Can y'all see that? Yeah. Actually, this side of the board's always blurry. I'll rewrite it. It's nicer. And then you're basically just averaging out all the vectors in J1. If you haven't seen this notation before, all this means is that we're summing all the vectors x such that x is in J1. And J1 is just the collection, in this case over here, of all that. Dot, 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 do that for each of the centers. And this is just the cardinality of J sub k. Cardinality is the number of vectors in there. Okay. And again, we're just summing all the entry. So you know how to add vectors. You add vectors component-wise, and then you get a resulting vector, and then divide that vector by the total number of vectors in that set. So we'd add all these vectors together, and then divide by 1, 2, 3, 4, 5, 6 for C2. That would be a new center C2. Okay, and part 4. Now, there's many different stopping conditions. In fact, your textbook introduces what's called a loss function, I think. I don't see a need for that right now. I'm going to say, I'll just say, repeat 2, then 3, until the centers don't move very much. That's how I'm going to define it. Don't move much until all the centers don't move much. And there's various ways that you can measure that, right? For example, you can look at distances between your old centers and your new centers. And then just look at the 2 norm distance between old and new. If your centers aren't moving, they're not being updated, then you've, in a sense, converged. Okay. So do you see like what this is going to do to your sensors? Like originally you were like way over there, right? Like center 1 is right there. But when you average out all of the x values for these vectors, so I need someone to speak up. Like we have vector, 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 vector. All of those belong to the center C1, right? So the average x1 value, so this way, x1, the average x1 entry, the first entry, where is it? Tell me when to stop. Where do you think it'd be?
Stop.
Yeah, I would say that like for all of these vectors there, the average x1 would be like right about there. Okay. All right, so I'm gonna do the same thing for the x2 axis. So tell me when to stop when you think I made it to the average y value.
Stop.
Yeah, that's what I was gonna say, somewhere around there. So now up over, it looks like now there's my new center.
So I'm confused. Is this actually finding clusters, or is it just making it to where each center has an equal amount of vectors assigned to it?
It's not going to be an equal amount. In fact, look what happens with these guys here.
Are we just like essentially lessening the distance between the center value and the actual values of the cluster?
You're, um, you're trying. Okay, let me describe it. It's almost like you're moving your center. Yeah, you're always moving your center towards the center of a group. Right? That's always going to happen. You're always going to go towards a group. So let's look what happens when I move the other ones now. So hopefully everyone can see how the centers are going to move. So this center, it's probably going to move a little bit to the left, maybe a little tiny bit, and then it's probably going to go to like there, maybe, right? So I have to remember exactly where those marks are. It's like something like that. The new center would be like right there. Okay, and then this center would probably have moved to the x direction definitely, and probably stayed around there. Okay. So now let's update. So we need to repeat 2 now. So assign each vector in our data set to the closest center. Look what happened to that one now.
It moves to the different C1.
Right. Now it's over there. Right now it's with C1. These still are there, but because that one was closer to this group, right? That one was closer to this group. When that one moved to the center of that group, that one became a part of it. Does that help explain that? What's going on with it? Like, that one was originally is closer to this group, right? So when we moved C1 to be the middle of that group, then that one belongs with that group, as it should be. If you look at the picture all together, it kind of is together like that. And yeah, you can see it. So
I have a quick question. How do we know how many centers to choose? Like if we have a vector and say there was like another different cluster.
So this is a question. This is a very good question. I want to make sure that your book doesn't. Your book teaches this a little bit different than how I typically teach this topic, so I have to be careful about how I say my words right now. I'll say it how I normally do, and then I will reference back to the notes. So when you choose a value for k, you can give a measure of how good the clusters that you end up, how good that is, right? And basically that measure is, hopefully I can fit it right here. Okay. I think this is the notation we'll use, J plus maybe. Okay. So this is going to be equal to, what do they use? I'll just hold the book up instead of trying to wing it. All right, so suppose that there's capital N vectors in your data set. Each one is going to be assigned a center, C1 through CK. And this is not exactly what your textbook writes, but this is still correct. You take the average squared distances. So this is like X. I really should just introduce this notation now. So I want to write down a big list of X's to represent my data, but there's an X1 entry, there's an X2 entry for each of those. So bear with me, I'm going to use superscripts to count these vectors. So the superscript just means that's the first vector in the list. The notation is a little bit messy here. I'll just say Z1. And I'll tell you what the Z's are in a moment. So this is squared, that distance squared, plus dot, 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 plus the distance from Xn to Zn all squared. Okay, so what are the Z's? I'm going to say let Zi denote the center that Xi was assigned. Does that notation make sense? So the superscript just means it's just that's the first vector in the list of data. That's the nth vector in the list of data. It's just counting them. So to avoid confusion between subscripts and the entries of the vector, which is an annoying thing that pops up a lot. So this is going to measure the distance from your vector, your data entries to the centers that they've been assigned, squaring them, and then averaging them all out. So the better choice of centers that we have, the closer these values would be, the lower this total number is. This is like a measure of error. In fact, that's the first time I've said that this semester, actually. It's like measures error, in a sense. Is the closer these are approximated, the closer our centers are to the data. So if you chose K to be 1, only one center. If you chose K to be 2, you have 2 centers. If you chose K to be 3, you have 3 centers. And you run this algorithm 3 different times for those 3 centers, 3 different times for those choices of K, you're going to get different numbers for this. So you run when K is equal to 1 all the way through, and then you calculate this, you'll have a number. Then you choose K is equal to 2, run the algorithm, and then calculate this, you'll have another number, probably better than K is equal to 1, right? And you can study how the error changes as your K changes. Now, obviously, you're not going to choose K to be huge. Like, you're not going to choose N centers. There's a trade-off. And this is something, again, that you will talk about in much more detail when you take a machine learning course. That's like way down the line. Here, we're just trying to show, I'm trying to introduce you to a very important algorithm using the most minimal amount of information possible. And what is that? It's the idea of distance between vectors. If you know what vectors can do, right, and how to operate on vectors, you can immediately start doing data science, right? You can immediately start designing algorithms to look at data and to analyze data. Okay, so I think that should be the theory behind everything. Now let's go ahead and implement, let's program this together from scratch. So I'm going to pause the video and, all right. So I just posted the Iris data set. That'll be the data set that we're going to use. Now, this data set, where did it go? Oh, here it is. This data set is a labeled data set. So we know the labels, but we're just going to pretend like we don't know the labels and just use the raw feature vectors. So import your standard packages, pandas and NumPy, and then also a matplot library. Matplotlib, .pyplot as plt, and then I'll say iris is equal to pd.read csv.
Davila, do you mean to be scaring your other screen?
Oh, does it not? Oh, good call. Surprised no one brought that up sooner. Okay, so what did I call this data set? It's called iris dataset.csv. Okay. Okay. And then let's take a look at it. Okay. So this is a very famous data set. This is probably your first time seeing it. So this is a CSV file consisting of 4 measurements for 3 different types of flowers. All the same sub-iris flower, but different species of the iris flower. So there's Setosa, Virginica, and versicolor as the 3 labels. And their measurements are given here. Okay, so as before, we don't have to necessarily use all of the data. So to make it look more like the plot that we have on the board, I'm just going to use 2 features, and I don't know which 2 I should use. Maybe, so x is equal to maybe gray, and I'm going to pass that x0. There is like a faster way to do this. I just don't feel like looking it up right now. Okay. So I'm going to make NumPy arrays, which are like vectors, as you know, for x and zip iris dot maybe sepal length, maybe. Yeah. And then maybe iris dot maybe sepal width. Okay. Let's see. So we have this collection of vectors. Okay, so maybe we should plot it real fast. Let's do that. Scatter. So x0 for x in big X is our first entry, and then x1 for x in big X. So let's scatter that. Okay. So it looks like we have some possible clusters. By the way, if you want to see the real clusters, these I'll just show it to you real fast. So we know ahead of time what the clusters look like. I know that the first 50 entries of this are of one species. I know from 50 to 100, that's another species. This goes up to, you always go one further. So 50 to 101. And now the last 50 is the other species. Am I doing these indices right? We'll find out. 100. So those are the actual different species. I kind of don't like that. Let's see with some other more. No, this should be fine. We'll just do this. Okay. Okay, so we need a way to take a collection of centers and make new centers, right? So I'm going to write a function to do that. So def make new centers once I have centers. So it's going to take in a collection. Let's call it centers. So what do we want to do? So for each of them in there, each thing inside of center. So I'm going to go ahead and write that out here. So maybe, let's just go ahead and do this by hand at first. So not by hand, but like hard code it. And by that, I'm going to say, I'm going to take k equal to 3. Also, we want to forget that we have what the actual clusters are. We're going to forget that, and we're going to see if we can use this method to find them. Okay. Okay, so make k is equal to 3. And then I'm going to choose some random vectors from my list to be the initial centers. So I'm going to say, actually, I need to try something real fast. Just because I forget off the top of my head. np.random.rand int, is that it? Okay, that's how you get a random index. So I'm going to say that centers equals x. And now I'm just going to get a random one out of there. 150. So it's going to be a random index chosen between 1 and 150 from x. And I need to do that how many times? 3 times. Okay. So where are my centers? Those are my centers. So now let's just kind of see where they're at in the plot. So I'm going to plot the original data, and then I'm going to PLT.scatter the centers. So we have, this is our first point. So let's plug that in there. Say color equals red. And what's my next point? 5.0 and 3.4. Maybe I'll make this one like green or something. And then my other center is going to be 5.1 and 3.8. Oh, those are really close together. Oh, yellow maybe? Oh, and the green's not showing it. Maybe orange instead of green. All right, so those are our centers. Okay, we have red, orange, yellow. Okay, obviously these are going to be clustered red at first. So, oh, that makes me think that we need to assign centers to these, each of these vectors. So I'm going to need a function for distance between two vectors x and y, and that's going to return the 2 norm. So the square root of x times y, x inner product y. Okay, and now I need to assign these things. So maybe centers. So this is going to take in your feature vectors and your centers. Okay, and it's going to return, maybe I'll return a dictionary pointing towards all the, no, what can I do? Let's see, maybe we can say, oh, I know exactly what we can do. So, all right, for each of the feature vectors, I'm going to make a vector that's k long, where the 0 entry is the distance from the vector to center 0, and the 1 entry is the ith entry is the distance from that vector to the center. So the center I. So how can I do this? So maybe, I'll say Z. Oh, that's perfect, because that's what we were using on the board, Z to be the assignment. Okay, so then we want to say for I, or maybe X in feature vectors. Again, I'm doing this on the fly right now. This is kind of just me hacking this algorithm together. There are obviously better ways to do this, or maybe not obviously, but there are. It's just I'm hacking it together for the purpose of showing you how I typically will start trying to implement one of these things. So what am I going to do? C dist equals to this. And then for C in centers, I'm going to put into this this list here the distance from X to that center. So I'm going to say Z dist dot append distance from X to C. Okay. So that will do what I wanted. It'll put in the ith entry the distance from X to center I. And then after you do that, I want to put that list into Z. Okay, so I can say Z dot append Z dist. So all that does is say each of the feature vectors, maybe I'll make this a dictionary so it'll be a little bit more clear. And then I can just say Z X as a key is equal to, no, I don't need to calculate all the distances. I can do this one at a time. So I'm going to make this just like, we're always going to have at least one center. So I'll say that distance from X to centers 0. And then for C and centers, if needs to be assigned somewhere too. C I is equal to 0. So this is going to be the numeric label to the center we're going to. And again, this is just trying to illustrate to you. You won't be asked to program this on your own. I'm just trying to illustrate this to you so you can try to do it on your own. You can try at least. Okay, so for I, comma C and enumerate centers. So that basically just puts I together with the corresponding center in there. If the distance from X to C is less than Z distance, Zi is equal to I. So I just hacked that together so bad. So for X, for each of the vectors in there, I assume it's closest to the 0th center. I assign Z distance to be the distance from that X to the 0th center. And then I enumerate all of these centers. And if the distance from any of the newer centers is less than this, then I update my I and I update my Z distance. And just repeat. So it finds the minimum distance one. That's actually like a standard programming type of problem to find minimums like that. Okay, so after I do that, I have my dictionary up here that I want to assign things to. So I'll say ZX is assigned to ZI. Okay. And that'll do that for each of them, right? But I want to make my J's, right? My J was the collection of all the centers. Or the collection of all the feature vectors that were assigned to the centers. So let's see if we can figure this one out. No, not yet. We don't need that. We can do that in another function. I just want to do this to make sure it works. So then I'm going to return Z. Okay. So let's see what this does. So let's assign centers. Our feature vectors were in X, and I think I called the centers centers. Let's see what this returns. something is off here. Those are my centers. There's definitely something in there. Okay. Oh, I never populated Z. That's what's wrong. It's dumb. Z X equals all right. Okay. So that's going to assign me to that center. Okay, so I'm going to run that cell. Oh, I can't pass that in as a numpy. I can't pass in a key as that. So I guess I'll just have to put it as a list and then do z dot append. I'm going to put in a list where the first thing is X and the second thing is the centers that it was assigned to. Z, that should have been a ZI anyhow. There. Okay. All right. So what did it do? So the first entry in each of these lists, like this right here, that's a vector from our data and it has been assigned to that center. This has been assigned to that center. Okay. This has been assigned to that center. This has been assigned to that center. So it's doing what we want. But now it'd be nice if we could say, what are the J's? Like, how do we collect all the vectors that belong to the 0 center? What are all the vectors that are collected with the 1 center? Okay, so this definitely does something nice. So then, oh, I know what to do. It's not going to be pretty, but I kind of want to put it in another function. So I'm going to say collect assignments, maybe something like that. So it's going to take in your feature vectors and your centers. And immediately it's going to say that I'm going to get this thing right here, this guy right here. So maybe assignments equals assign centers. God, I think this is like one of the slowest ways I've done this, but I'm kind of just hacking it together again. So now, new, so J is going to be equal to this empty, and then for underscore and range length of centers, something like that. I'm going to put into J large lists containing all of the arrays that correspond to being assigned the ith center. So by that, just I mean, oh, this. Okay, I'm going to clean this up. This is ugly code. So for I, C, and enumerate centers, I'm going to say J temp or something is equal to the list of X for X in assignments if X1 is equal to C. Is that all I need? And then Yeah. Yeah. So I guess I could just make this a dictionary to make it a little bit more readable. And I can say JI equals to J temp, and then return J. All right, so let's see what this does. Collect assignments. Everything we have is in X, and then centers is just in centers. Oh, missing an N. Yep. Oh, there's a weird truth value thing here. So basically, I'm just trying to get this to be equal. So this is the, like, this assignments thing here. I'm just gonna like completely butcher this lecture today. Typically code faster than this, but at least you get to see me like figuring it out on the spot. So this vector is assigned to there, this vector is assigned there, this vector is assigned there, so forth and so on. So let me just test something real fast because that error was weird. So I'm gonna call that A, and then A0 is this first array right here, 0, good. So I know that's the same as the next one. Oh no, there's the 1 entry. Oh, not assign. Oh, is that all I did? No. There. True. So that's what it's doing. It's not returning. It's not returning a true statement here, so that's why it's throwing it off. So there's probably a NumPy function to do this. NumPy. NumPy array is equal. Oh, is it that? NumPy way. Okay, so it's this. So I just copy that, come back over here, and then now because these are NumPy arrays, I'm going to pass in here x1, and then here this is the center C. So it's basically seeing if that thing was assigned to that center. All right, so let's try that again. Oh, I didn't close off when I made that new there. Yep. So this better work now. All right, so let's test it out. Okay. So everything looks like it's been assigned. So it looks like nothing was assigned to the 0th center. So like 0 is nothing. These are all the 1s. Oh, actually, sorry. There, this should be the 0th entry. Okay. So those are all the ones that have been assigned to center 1, and these are all the ones that have been assigned to center 2. So they're all assigned to center 1 for some reason. Okay. Why is that?
Even if we chose bad centers, you would kind of expect every single one to have at least a few vectors, right?
Let's make another one. Let's make another. So like, yeah, so I made new centers. Let's see what happens now. Now they're all assigned to 0. Interesting. All right, let's see if we can find out why this is doing it. It has to be in this function here. Okay, so I'm just gonna scratch this thing right here. I'm gonna do this better because I wasn't happy with it when I was doing it, and now it's making something off. So, oh, wait a minute. Oh, it's in my distance function. What am I doing? It's x minus y times x minus y. That's the distance function. How did I not catch that? I bet you it's going to work now. I'm still not happy with this function, but I bet you it's going to work. There, those are all the centers for, yeah, what I was doing was taking the square root of I was almost like minimizing the angle between the vectors, and we'll get to that next time, but you can see now that each vector has been assigned center. So so how can this is just so gross to do it this way, scatter. What was I gonna do? X0 or Xn. So these are all the ones that have been assigned to the first one. And then I'm just gonna copy this and then paste it. And so, but now I just have to make this the 1 entry. And then what were my colors I used for the, so copy that, bring it back down. So red is that color. So okay, then close off that plot. And then now I'm going to do the same thing, but now for all the ones with been assigned to 1. Make these all orange, and then now I'll do the same thing for all of those assigned to 2. Make those yellow. Oh, these are the wrong centers. Oh, there's a very fast way to do this. What are the centers again? Because I changed my centers. So 5.1. Yeah, so 5.1, 2.5, 5.6, 2.7, 5.2, 3.5, 0.5. Let me look up something real fast. Matplotlib. Box marker. Marker equals that. Maybe I want a square for these guys to distinguish them. So marker equals, does that do it? Yes, it does. Marker equal this guy. And then finally marker that guy again. I hate that. I prefer single quotes. So I'm just picky about that. Where's the orange one? So there's the orange marker. I mean, so orange is center 1, red is center 0, and then yellow is center 2. Okay, so now we just need to update update the centers. So you have you throw in some centers, and we're going to say for and I guess we also need the feature vectors. Yeah. Feature vectors. So we're going to collect the assignments first, and we'll call that like Z or something. So that gives me a dictionary pointing towards all the appropriate vectors. So then I can say for I X and enumerate centers. CI equals, can I, so real fast, I'm gonna check something before I do it. I'm so used to programming in Julia, I always get things mixed up when I switch over to Python. So I'm just gonna see something real fast. So D is equal to that. I'm just seeing if I can sum the vectors, sum NumPy vectors. Can I do that? Oh, good, I can. So this is going to be the sum of Zi divided by the length of Zi. So that's the average vector. And then centers I is going to now be updated to be Ci. And then just return centers. Hopefully that works. Update centers. I'll just call this new centers equals, and we're going to throw in X in our old centers. Hopefully it works. Okay. I'm going to make sure there's a difference here. They look the same. Oh, it's because it's changing the centers. This is annoying. This will there, run that. So now they're not moving anymore. I think it already converged. Yeah, let me start this process over again with some just random centers. Okay, got that. Okay, So what are the centers now? Okay, so now I'm going to say new centers, these, and then what are the new centers? What is happening here? You see how they're the same? Oh, I was returning centers again. Dang it. New centers there. So now I never changed anything. So there, they changed. So these are the new centers. Okay. So let's just like update this again. So let's start from the beginning and make a nice little picture. Copy that. Okay. Now this is going to be I'm going to choose better marker. So these will be really distinguishable now. Now I'm going to make the third group green instead of yellow, because yellow is hard for me to see. And also, instead of doing this a bunch of times, I'm going to say for C and centers, C0, C1. For I, I'm going to enumerate this. I'm getting somewhat fancy on this, but it's okay. Y'all will see this a bunch. Red, orange, green. I'm just doing this in a loop so I can not have to worry about things as much. Okay. And then I'm gonna make new centers again, and we're gonna start from the very beginning. Okay, so. All right, so here we have our original centers right there. All right, so now what I'm gonna do is I'm going to update these centers and repeat. Okay, so there's our original picture. So now I'm gonna just update my centers. I'm not gonna say new centers, I'm just gonna say update like that. Okay. I see how there's been a change, right? Looks like the square center here, there's a center there, there's a center there. And then I guess we'll just do this one more time and see what happens. Oh, I apologize for today's lecture being a little bit off. I've been kind of ill feeling lately, and it hasn't made thinking too easy. I have some more updates. Okay. And let's see if we get any more changes. If I just do this again. See how that red center is slowly starting to move over here? Let's keep on going. I'm curious now. If I do it again, it looks like it's still moving that way. The red center is starting to really move. You see that? Just gonna keep on doing this. See, it's starting to pick up some over there. I'm just gonna do this a bunch of times for underscore in range. Let's just do this like 50 times. So I don't have to keep on doing this. So now there. And then after I do that a bunch of times, then I can plot and see what happens. Yeah, 100 times, whatever. So update the centers a bunch of times and then plot. All right, and then if we keep on doing this, doesn't look like there's much movement anymore. Okay, maybe one more time. All right, so that's the clustering that we got by updating this over and over again. Let me go back up here, way up here. Where's the original? Copy, go back down. So let's see what the actual clustering is. Color equals, I don't know. I don't know what the colors are, actually. I don't know which of these groups each of these belongs to. Yeah, look at that. That's pretty cool, huh? I know it was kind of a pain to get it to work, but it was a first try, first go without really much to help us out. But yeah, that's not bad. We definitely clustered all of those guys, right? Now these over here, there's mixing in there, but still it looks like we did pretty well in getting those versus those, right? So one last time, I'm going to go back up here and I'm going to change the features that we looked at just to see if we get anything better going on. So maybe instead of sepal length, maybe I'll do petal length or something. So we have different data now. Oh, wow. But that looks like it could be clustered a lot easier, right? So I've changed the features and we're using petal length instead of sepal length as the first entry. So let's see what happens if we go back down here and do the stuff again. So make some random centers. Those are the random centers starting off. And now instead of like doing this one by one, I'm just going to go down to that loop I made to update the centers a bunch. Yeah, so here, and see what happens. Yeah, and it looks like it clustered those pretty well that time. Okay, so that is the k-means algorithm. I'll go ahead and stop the recording there.